Yep. Hello, my name is Timothee Redarce from the Department of Hydrogen Energy Systems in the Graduate School of Engineering of Kyushu University. So I will be sharing my presentation. So the presentation of my thesis is called the breakthrough of a 900 megapascal barrier of fatigue crack growth resistance in BCC stills in high pressure hydrogen environment. So as you may know, with the decarbonization efforts done overall in the world, hydrogen may have an extremely important role to take in these actions, and we can call that hydrogen society. There is a need for an increased commercialization of those technologies, and one of the drawbacks on that is that hydrogen embrittlement is a major issue against these technologies. We need, there is a way to counter hydrogen embrittlement, but it's using very expensive materials. So there is a need for lower cost materials that can withstand very difficult hydrogen environments. So what is hydrogen embrittlement? There's mainly two big impacts. The first one is a loss of ductility of materials. So here slow strain tensile test was performed, and we can see there's the big difference. So here from a test made in a normal air environment, like around us now, and one in 83 megapascal hydrogen environment. And we can see that there is a big difference in the shape of the break, of the part where it broke, and it's due to the loss of ductility implied by this hydrogen embrittlement. The other one is a fatigue crack growth acceleration, so it's very well tied with the loss of ductility, but we can see that here in the materials used nowadays to counteract hydrogen embrittlement, there is not that much difference in the crack growth rate while it's being tested in air, so here the black line, or in high hydrogen environments, here the red line. So this is quite good results, but they come from very expensive materials. So here I show an idea of prices can be over 10 euros per kilo for this stainless steel. And then on my thesis, we're focusing on more cheap materials that would be for now at the raw price around 1 euro per kilo, for example. The main problem is that here with the fatigue crack growth, we can see, so again in black is when it's tested in air, and in red when it's in hydrogen environment. And we can see that the behavior, it's not good at all in this in hydrogen environment. Then about the strength design of components. So nowadays we have two main ways of doing it. It's either the design by rule or the design by analysis. The design by rule is mostly theoretical, and to make sure that there is no safety issue, we had a very, very important safety factor that can be up to 4. The other way of designing is using the design by analysis. So this time we determine the thickness with partially theory and partially experimental results. And we can also use a much lower safety factor, meaning that when designing the components, the design by analysis allows technically for the use of a less amount of material. So the target of the research was to, here in this graph, move this zone more to the right with higher tensile strength. So this graph shows the relative fatigue crack growth of metals in hydrogen environments. And we can see that the fatigue crack growth is quite okay until a tensile strength of materials that's over 900 megapascal. And from that here, the fatigue crack growth rate increases a lot. So the goal will be to lower those, so to have this knee appear at, we are aiming for 1 gigapascal. With, if it's possible, we want to try to go to up to 1.1 as a goal. And the way to do this, we decided to focus on the type of osforming treatment. Osforming is, yes, a type of heat treatment that also combines deformation during the process of making the material. And so here in this graph on the right, on the graph A, it shows a classic microstructure, I say, and one that is not OS-formed, just a basic heat treatment. And then in B, an OS-formed microstructure. And we can see that it's more wavy, so in a way it increases the surface, for the amount of surface where there is a force applied on, so releasing pressure and hopefully increasing the strength of the material. And some research have been made, a lot of research have been made on hydrogen embrittlement. Some research have been made on OS-formed materials, but there is currently no other research that combines both OS-formed materials and hydrogen embrittlements. So we'll do that by doing classic compact tension specimens to test the fatigue crack growth with much different ways of testing in hydrogen gas, in air, different pressure hydrogen gas, of course, different test frequencies. And then there will be observation of crack propagation path and crack tips, and to try to determine and analyze the proper propagation of these cracks. And now, so due to the current situation where since I started my doctoral program, I have been stuck in France because borders of Japan were closed. I am still in France now, but it's finally reopening. So within a few weeks, I should be able to come and launch full-scale experiments and observation. But for now, I've been investigating a lot into machine learning, learning a lot about this technology to try to help us either identify microstructures but mainly to help us design microstructures to help us work around the increase of the knee that I showed you in one of the previous graphs. And so overall, the importance of this study, so if brought with success, we would be able to increase the capacity storage of vessels and also their safety, lower the cost of general hydrogen technologies, and also decrease the weight of components. This in a way would, I hope, improve the public's opinion about hydrogen technologies, also the interest and the trust, and mostly for companies too. And all of those efforts will lead to the acceleration of the transition to a more decarbonized society. Thank you very much for your attention.
のある方は挙手機能をお使いください。産業界の皆様いかがでしょうか。手は上がってないようですが、ありがとうございます。上がってないですかね。上がってるか。伊藤先生、上げてくださってますか。
はい。
はい。
Timothy, can you hear me?
Yes.
Okay. Nice to meet you again. Okay. So just a general question. Today you suggest 900 megapascal.
Yes.
As for tensile stress, right?
Yeah. This is today.
Okay. So my question, what this number mean? So I wonder, this is some critical something. I'm not sure the significance meaning of this number. So could you explain?
Yeah. So it's the tensile strength of the materials used. So with different treatments applied, we obtain for about same composition, different tensile strength. And while doing this compact tension testing, we obtained this graph. And the way to order which materials we were working on was through their tensile strength, because the tensile strength represents in a way the toughness of its material. The strength, basically, as it said in the name, the strength of each material. And so we see that when the strength of the material is over this 900 megapascal zone, we have a very, very high fatigue crack growth rate. But when the material has its tensile strength that is lower than 900, it's quite, it's a decent fatigue crack growth rate. But yes, the tensile strength, to make it very simple, would just represent the toughness of the material.
Okay, yeah, I understand. But as you know, if you change the, okay, how do I say, design of machine,
yes,
we can use some cheap material within 9 megapascal barrier.
yes.
Is this impossible? I mean,
So,
yeah.
yes, sorry. So here we have this 900 megapascal barrier. It's with these two metals. And so if with them we have a design, for now it's the typical microstructure we get from heat treatments. If the strength, again, is over 900 megapascal, it will be on this part of the curve. But with this other way of treatment, so the os forming, we may be able to have metals that have a different structure. And even if their tensile strength is over 900 megapascal, the fatigue crack growth rate will stay in this general area.
Okay.
If we are able to be there, it means that we can actually design very high high capacity containers.
Okay, I understand. Thank you. My following question will be shown in some chat box. Okay.
Okay.
Okay. Thank you. Anyway, bye-bye.
Bye. So thank you for your attention during the presentation, and thank you for having me.